The interplay of proteins and peptides with solid surfaces is a fundamental phenomenon with implications for nanotechnology, biomaterials, and biotechnology. The first step in comprehending of such phenomenon is revealing fundamental physicochemical constants such as adsorption constant, Gibbs free energy, enthalpy, entropy, and limiting adsorption, which may be evaluated through establishing adsorption isotherms. However, adsorption from liquid phase is restricted with kinetics, surface capacity, pH, and competitive adsorption, which all should be cautiously considered before setting the experiment. In this video, my colleagues Elena Korina and Sergei Neifert will present the physicochemical study of dipeptide adsorption on titanium oxide, covering preparation features that will help avoiding hidden reefs which researchers may face while performing relevant experiments. Place 183 mg of dipeptide in the sterile polymeric test tube and dilute up to 38 ml with double distilled water and dissolve at the room temperature under vigorous stirring. If the dipeptide doesn't dissolve in double distilled water under stirring, place the dipeptide solution into the ultrasonic bath and sonicate for a few minutes. Adjust the pH of pre-dissolved solution of a dipeptide to 7.4 by cautious adding solution of mess or sodium hydroxide to the dipeptide solution upon stirring at room temperature, and monitoring the pH with a pH meter. After adjusting the pH, fill the test tube with a double distilled water up to 40 ml to make the final concentration of 16 millimolar. Prepare dipeptide dilutions with concentrations between 0.4 and 12 millimolar by diluting 16 millimolar dipeptide solution with double distilled water. For example, in order to prepare 8 millimolar dipeptide solution, add 9 ml of double distilled water to 10 ml of 16 millimolar dipeptide solution. After dilution, adjust the pH to 7.4 by adding dropwise solution of mess or sodium hydroxide to the dipeptide solution. After adjusting the pH, fill the volume of the solution up to 20 ml with double distilled water to make dipeptide concentration of 8 millimolar. Other dilutions of dipeptide stock solution are prepared accordingly. In the end, we get the row of dipeptide dilutions ready for absorption studies. Prepare 10 millimolar mass buffer solution. Adjust the pH to 7.4 with dry sodium hydroxide upon stirring, and monitoring the pH with a pH meter. This solution will be used for the Zoll preparation. Grind approximately 200 mg of nanocrystalline titanium oxide in a mortar for at least 5 minutes. Weigh 40 mg of ground titanium dioxide nanoparticles into the laboratory flask. Put the flask into the sonication bath using the laboratory stand. Add 20 ml of 10 millimolar mass buffer solution into the flask with titanium oxide. And sonicate in an ultrasonic bath for 20 minutes. Add 1 ml of sonicated Zoll of titanium oxide to the 1 ml of each dipeptide dilution concentration. Set the thermostat to the desired temperature. Place the series of adsorption samples to the thermostat for 24 hours to achieve the adsorption equilibrium. Occasionally agitate titanium oxide dispersions during the thermostating. In order to avoid temperature-induced re-equilibration, take out one sample from the thermostat for filtration at a time. Take a sample of the dipeptide solution from each glass vial with a syringe. Remove the needle from the syringe and put on the syringe filter. To filter the dipeptide solution into the glass vial. Repeat with samples of other concentrations. Now these samples are ready for analysis. Make the 50 ml solution of TFA in acetonitrile. Spike 0.34 ml of TFA in the measuring cylinder and adjust the volume of solution to 50 ml with acetonitrile at room temperature. Prepare the derivatization solution. Spike 299 microliters of phenyl isothiocyanate and 347 microliters of triethylamine in the measuring cylinder, and fill the cylinder up to 50 ml with acetonitrile. Prior to the high-performance liquid chromatography analysis, derivatize the samples with Edmonds reagents in the chromatography vials. Mix the 400 microliters of the sample with 400 microliters of derivatization reagent. Heat the samples at 60 degrees for 15 minutes. After heating, neutralize the samples with 225 microliters of TFA solution and wait for a few minutes to cool sample to room temperature. Use HPLC analysis to determine the concentration of the dipeptide solution before and after the adsorption. Start the analysis of the samples with the necessary conditions which are set by the software. The dependencies of adsorption from the equilibrium dipeptide concentration after adsorption, the adsorption as isotherms, were plotted according to the obtained experimental data. The measurements of dipeptide adsorption were data processed using the Henry model. The equilibrium binding constant was obtained from the slope of the dependence of dipeptide adsorption on the dipeptide equilibrium concentration. The 1/2 equation was used for determining the standard Gibbs free energy for each temperature. Plotting a graph of free energy versus temperature, we determine the enthalpy as intersection of the linear graph with the free energy axis for dipeptide. The change in entropy for each temperature was determined from the fundamental equation. The calculated values of the equilibrium binding constant, standard Gibbs free energy, enthalpy, and entropy for dipeptide are presented in the table 1. Adsorption isotherm construction from depletion data remains to be the most available methodology that does not require expensive setups, providing exhaustible physical chemistry data for literally every soluble sorbate. Combined with spectroscopic or computer-based data, it may reveal fundamental structural features of complex behavior of biomolecules upon contacting the inorganic surfaces.